So here we are at our last lab lecture for the semester. We'll be covering entropy, free energy, and chemical equilibrium. So you should see some familiar concepts that we've discussed in my narrated lectures now, or in homework and other things that we've covered. So the background for this lab is basically we've discussed the relationship now of delta G with K, and that relationship's just the delta G equals minus RT ln of K. And as far back as last semester, we had discussed the relationship of delta G with delta H and delta S, or the enthalpy and entropy. And what we're going to do in this particular experiment is we're going to look at experimentally determining what K is at several temperatures. And if we have the value for K, we know what temperature we're at, we can find delta G. The next thing we can do is we can graph that delta G versus the temperature, and we can generate a line that's going to have a slope of negative delta S and a y-intercept of delta H. So we're going to just look at a hypothetical reaction. I just made this up and see how we can do this analysis. So let's say we have a reaction of A and B going to C and D, and this is the data that we get from the experiment. So we find Kc is 3.9 times 10 to the minus 8 at 275 Kelvin, 2.58 times 10 to the minus 4 at 325 Kelvin, and 6.41 times 10 to the minus 2 at 370 Kelvin. If we have those values, each row, I can go ahead and calculate what delta G is. So where you see that 3.9 times 10 to the 4 joules per mole, that was just generated from me doing minus RT, ln of K. The T was, of course, the 275 Kelvin. The K was the 3.9 times 10 to the minus 8. And the R is our 8.3145 joules per mole Kelvin. So we just calculate that whole column from using the previous entries to the left of in the equilibrium and the temperature. So if we do that, we can graph it, the delta G versus the temperature. And I can go ahead and do a line of best fit there. We see we have a slope that's negative in this case, and we have an intercept that's positive. If we look at the y-intercept we're getting there, we get 1.27 times 10 to the 5 joules per mole. We can quickly translate that to 127 kilojoules per mole. And this is a endothermic reaction if that's the case. And that kind of makes sense, with the reactions favoring more products as we turn up the heat and turn up the heat and turn up the heat. And that's exactly what we'd expect from Le Chatelier's principle, because in an endothermic reaction, the heat is on the reactant side. We go ahead and look at the slope. It's negative 321.85 joules per mole Kelvin. Remember, the slope is negative delta S, so if we wish to find delta S for this particular reaction, we have to flip the sign there, so we get 321.85 joules per mole Kelvin. And so that's effectively what you're going to do. You need to find 3 different values of K. I believe that's what Dr. Miller had done in her write-up that she sent out to everyone. And then you'll find those 3 values of K, and you'll have to just basically find the delta G's that are correspond to them, graph them, find the delta H and delta S of the reaction. And that's the real overarching goal here. So let's look a little bit more at the reaction that we're choosing to investigate here. And we're looking at calcium hydroxide in solution. This is a sparingly soluble salt, so it gets a KSP. We would write that KSP as the calcium times the hydroxide concentration squared. So if we are going to calculate the KSP, then what we need is to be able to find the equilibrium concentrations of the calcium ion and the hydroxide ion. And how exactly can we do this? Well, remember, if we have a saturated solution, then we know that it's in equilibrium with the salt that's sitting below. And so we have dissolved ions that are floating around in the solution. So what we're trying to do is we want to find the concentration of that hydroxide in the supernatant. And remember, that word just means the liquid that sits above the insoluble salt or a precipitate. And so just taking a look at this, just notice you have that, calcium hydroxide sitting at the bottom, and then you have calcium ions, you have hydroxide ions floating about. And so our wish is to find the concentration of that hydroxide. And so what we're going to do is we're going to take a sample of the supernatant, and it's going to have that same concentration of the ions that were in equilibrium with our precipitate. So the nice thing is now that if we get a sample of this, we know how to determine the amount of moles of hydroxide that are going to be in solution. We've done this with titration before, and we're going to do titration here. So we're going to have a standardized HCl solution. We'll have our sample of supernatant that we put below, and we'll be able to tell when we actually reach the equivalence point, at which point then we can calculate what the concentration of the hydroxide is in the solution. And since we know basically how to calculate what the hydroxide calculation or concentration relationship to the molar solubility, or X, we'll be able to figure out what the KSP is, and we'll do an example of that in just a little bit. The other important thing to remember is that I'm showing you one example here, but of course we're going to have several different temperatures that we're trying to figure out what the solubility or KSP is for those different temperatures. And so we're going to have to make several saturated solutions at different temperatures and conduct this experiment to see what the KSP is as the temperature is changing. And we know that if this thing is becoming more soluble as we heat it up, then we should see more hydroxide in those samples that were heated up before we acquired the sample of supernatant. If that still holds true, then the colder ones we expect less hydroxide. Okay, so just keep in mind, so we're going to do one where we acquire the supernatant at a hot temperature, one we acquired at a cold temperature, and one that'll be just something in between. So it's sort of a Goldilocks smattering of different temperatures to figure out how this equilibrium is changing. So I've given you an idea how to calculate the delta H, well, delta G, delta H, and delta S from a graph of different equilibria. And but we haven't done a calculation on how we would find the hydroxide and use that to find the KSP. So here's a practice calculation. So we already know how to find the delta H and delta S, like I said. So let's figure out how we find the KSP. And I'm going to do it for a similar salt, so you can still have to do some work figuring out how to do this for calcium hydroxide, but this should be a pretty good guide for you to figure out how to do it with, say, the salt of aluminum hydroxide. So we're going to consider the saturated solution of aluminum hydroxide. And of course, that's going to be the KSP that dominates that one, is just the aluminum times the hydroxide cubed. What we're going to do is we're going to take we're going to say that we take a 25 milliliter sample of that supernatant, and we're taking it at 25 degrees Celsius. We are then going to titrate it with a 0.1 molar solution of HCl. And we're going to say that it takes 22.1 milliliters of 0.1 molar HCl to reach the equivalence point. So how are we going to find the KSP from this data? So what's the concentration of hydroxide in our sample that we got from the supernatant? That should be our first starting point there. And we know that it took 22.1 milliliters of that 0.1 molar solution, so we can figure out using the stoichiometries, knowing that HCl and sodium hydroxide react in a 1-to-1 fashion, we end up with 2.21 times 10 to the minus 3 moles of sodium hydroxide. If we go ahead and look at the amount of volume that was initially contained in, we had a 25 milliliter sample, and so that gives us 8.84 times 10 to the minus 2 molar of that sodium hydroxide. So how do we proceed from here? So we know that the concentration in the supernatant must have been the same. It was 8.84 times 10 to the minus 2 molar. Well, let's just set up an ice diagram. So go ahead and set this up, and we know that we're going to get initially nothing for aluminum and hydroxide, and then we have X for aluminum, 3X for hydroxide. Summing those, we get X and 3X. So now if I look at calculating the KSP for this, I end up with 27X to the fourth. And if I look at the hydroxide, we can calculate what that hydroxide was. It should be just 3X is its equilibrium concentration. Well, we know what that X, or the 3X value is. It was 8.84 times 10 to the minus 2. So now just doing a little bit of manipulation there, we move the 3 over, and we end up with a third of our initial hydroxide concentration yields 2.95 times 10 to the minus 2 molar. So this is our molar solubility of this particular salt. So now what I can do is, if I know what that X value is, and I know KSP is 27 times X to the fourth, it should be pretty straightforward to calculate that the KSP for this value is 2.04 times 10 to the minus 5. If we wanted to slap some units on there, it'd be molarity to the fourth. That pretty much covers everything we're going to be doing in this lab. Hope it helped.